Hello friends, welcome to lecture 6.1. With this lecture we are going to start our journey on Wigner-Willi distributions. In the previous unit we discussed at length the concept of short time Fourier transform, the spectrogram, its properties, its limitations, its uses, and also how you could use a spectrogram for denoising. In this unit we are going to focus on the Wigner-Willi distribution and its variants, and in this lecture what we are going to do is we are going to look at the definition of Wigner-Willi distributions. Although I say properties here, primarily what I am going to do is illustrate how the Wigner-Willi distribution works out for different classes of signals, and towards the end we will show that the Wigner-Willi distribution results in interference, which is something that we will work on in the next lecture in 6.2. So, let us get going. Before we look at the definition of Wigner-Willi distribution, it is useful to recall that there are fundamentally two ways of calculating the energy density, whether it is a joint energy density or just the energy spectral density that we calculate using Fourier transform. There are two routes, the first route being transform the signal and then identify some kind of functional operation, typically a quadratic magnitude square, to get the energy density. Of course, justification has to be provided why that functional will result in an energy density. The second route is to compute the autocovariance function if you are looking at purely energy spectral density, but if you are looking at joint energy density, we are interested in computing the local autocovariance function and then take a Fourier transform of the same, which is essentially an extension of the Wiener-Khinchin theorem to the time frequency plane. Now, as we have noted on several occasions, spectrogram and scaleogram belong to the first category. In spectrogram you take the short time Fourier transform and then compute the squared magnitude, and in scaleogram the story is the same. You can compute the wavelet transform and then take the squared magnitude of the wavelet transform. The good thing about adopting this strategy for constructing the joint energy density is that you have a non-negative energy density, which is one of the key requirements that a joint energy density should satisfy to make some sense. However, we lose out on the marginality properties, and we have mentioned this even in the case of spectrogram and early on when we talked about the basics of time frequency analysis. Owing to Wigner's result, who showed that there exists no positive quadratic distribution that can satisfy the marginality property. So, what about Wigner-Willi distributions? Wigner-Willi distributions takes a second route, and this again we have noted earlier as well. That is, it computes a local autocovariance function and then takes a Fourier transform. As a result, by virtue of Wigner's own result, it satisfies several key requirements, especially marginality, but unfortunately it is not guaranteed to be non-negative for all signals in the entire time frequency plane. For a specific class of signals, maybe the WVD can turn out to be non-negative, but not necessarily for all signals. So, why should we really study Wigner-Willi distributions is a question if it is going to be non-negative. Well, what happens is, although it does not guarantee a non-negative energy density or distribution, the good thing about it is it serves as a prototype for several other distributions that came along. The moment Wigner-Willi distribution came about in the limelight, several other distributions as variants of Wigner-Willi distribution in an attempt to improve its properties or retain its properties have come about, and the unification of spectrogram, scaleogram and the Wigner-Willi distribution came about. So, that is a fantastic result. Therefore, it is good for pedagogical reasons at least to start off with Wigner-Willi distribution and then gradually see how we can make improvements to this, and one path of improvement leads to spectrogram, the other path of improvement leads to scaleogram. So, that is the idea. Now, let us move on to the definition of Wigner-Willi distribution. A quick historical background: Wigner conceived this distribution in about in around 1930s in the context of quantum thermodynamics, and Willy, who was interested in signal processing and in signal analysis, about 15 years later roughly rediscovered this in the context of signal analysis, where he was interested in estimating the instantaneous frequencies from the joint energy density. In fact, we will see later on that this Wigner-Willy distribution gives us a nice estimate of instantaneous frequency, in the sense that the average frequency that you compute from the Wigner-Willy distribution is nothing but the instantaneous frequency itself, whereas for the spectrogram and scaleogram you would have to compute ridges. So, now you understand why the name Wigner-Willy, although their discoveries were 15 inventions were 15 years apart. Okay, so look at equation 1, it gives you the definition of the Wigner-Willy distribution. It is a single integral. Unlike the short time Fourier transform, here the integral directly gives me the energy density. Again, compare in spectrogram, you will have to compute the short time Fourier transform and then take the squared magnitude. Here you do not do, you compute the energy density in a single step. So, what you are doing here is you have a product of x of tau plus t by 2 times x star of tau minus t by 2, and a Fourier transform of that is being evaluated, right. And what I give you in equation 2 is the frequency domain version of the same result. So, you can compute Wigner-Willy distribution either in time domain if you know the time domain expression, or if you know the frequency domain expression you can compute that in frequency domain. Again, this is a theoretical definition. Later on we will look at the practical aspects of Wigner-Willy, where I will give you expression for computing Wigner-Willy based on sample data. Now, what is happening here, that's very important to understand rather than just looking at the integral or getting intimidated by it. First point to observe is that this is a quadratic or bilinear energy distribution, because you are involving a product of signal with itself. So, there is a product of two terms, x of tau plus t by 2 times x star of tau minus t by 2, and I use a subscript xx to indicate that you are evaluating this energy density or auto joint energy density for the signal. You could therefore conceive of a cross joint energy density as well. Okay, so, that is the first thing, and secondly, that which is very important is that the Wigner-Willy distribution is a Fourier transform of a local autocovariance or autocorrelation. If you talk to a signal processing person, you would like to call this as autocorrelation. Strictly speaking, by our definition, this is actually a local autocovariance. Look at the similarity of this expression here with the definition of autocovariance that we had for the energy signals, periodic energy signals. The only difference is this is a local one, instantaneous, you can think of an instantaneous autocovariance and so on. Okay, so, let us understand what is happening here physically. When I am computing the Wigner-Willy distribution, I need to understand what is happening. Like in the short time Fourier transform, I know what I am doing. I am essentially breaking up the signal into a bunch of sine waves and determining how much each sine wave is present in the signal and at what time. Here what we are doing is, if you look at the product in the integral, what we are doing is at any point in time I am looking to the left and to the right of the signal. Assume that the signal is real, therefore x star is nothing but x itself. So, for real valued signals I am looking to the left and right of the signal over the same duration and then folding, that is I am actually computing what is the extent of overlap between these left and right segments, and I am not just looking at one segment, I am looking at all possible segments with respect to tau. So, let me show this to you or illustrate this to you on the board. So, let us take this signal here. So, let us say I have some signal, need not be periodic. What is happening in Wigner-Willy is that, let us say I am standing at tau, this is the tau, I am looking to the left, let us say this length is t by 2, and I look to the right for the same length, this is t by 2, and at this point, so you can say that our dummy variable right now is of course t. Yeah. So, I am standing at time tau and I am looking to the left and right and asking what is the extent of overlap between this segment here and this segment here. Okay. If there is any similarity, it will show up, even though that property may not be holding at this tau. So, that is one of the drawbacks of the Wigner-Willi distribution, as we will see later on, which does not give it the finite support property and so on, but that is the point. You are essentially looking at similarities between the segments to the left and right and over the entire duration. Of course, that entire duration makes it also non-local. Look at the integral. So, we have this integral. If you look at it carefully, you will realize that it is essentially looking at all possible segments and it is giving uniform weighting to all the segments. That should not be the case. If I am standing at tau, I should give more importance to the local properties. If I truly want to get the local properties at tau, I should give more importance to the segments here and less importance to the segments that are far away from tau. But the original Wigner-Willi distribution did not do that. It essentially gave uniform importance to uniform weighting to all the segments, and that kind of spoils the some of the properties of Wigner-Willi distribution. Later on we will study what is known as a pseudo Wigner-Willi distribution, which applies a window on top of the Wigner-Willi distribution, so that the window function will give more importance to the segments closer to tau and less importance to the segments far away from tau. Okay. So, that is the physical interpretation that we have, and the same interpretations can be applied in the frequency domain as well. If you look at the equation 2, the arguments are more or less the same. Despite some of these drawbacks, it has some beautiful properties, as we will learn today, and that is in this lecture and also the next lecture. So, let us get a feel of what is happening. Remember, the purpose of studying this distribution is to get the local features of the signal in the time frequency plane. So, we would like to know what is happening in the time frequency plane, what features does it capture, how does it capture, is there a smearing of the energy like we saw in spectrogram, or is there not. Now, as I show this to you on the slide, theoretically Wigner-Willi distribution offers excellent time frequency support, which means it does not smear the signal's energy in time or frequency. And you can show this mathematically. If I use this signal here x of t as a Dirac located centered at t naught, then the Wigner-Willi is also exactly centered at t naught. It is also an impulse. The most important thing is not just that it is centered at around t naught at t naught, but that it is also an impulse. So, an impulse in the signal domain transfers to an impulse in the Wigner-Willi or the joint energy, the time frequency plane as well. And I show this to you as a way of illustration here, by way of illustration, and the MATLAB code is given to you. I am using the time frequency toolbox once again. FM constant generates a signal. Of course, here first I am showing the sine wave or the complex exponential, but let us look at the later part of the code. I am generating an impulse here and I am computing the Wigner-Willi distribution of the analytic representation of the signal. It is important to actually use the analytic representation if you want to use this routine from the time frequency toolbox. Okay. So, you can see clearly that WVD has an excellent time localization. Compare this situation with what we had with the spectrogram. The time resolution of the spectrogram was limited by the window. Any windowing method will suffer from the drawback, whereas Wigner-Willi distribution does not. In fact, there is something else that we should learn by going back to the integral here, we are not definitely applying any windowing technique to the signal, we are not windowing the signal and then transforming, we are directly computing the energy density. Now, early on when we talked about time frequency analysis and basis functions and so on, we said there are two classes of basis functions, fixed basis and adaptive basis, for the purpose of signal analysis. Although Wigner-Willi distribution does not really involve a transform, sometimes it is argued that there is a transform involved of the signal. So, let us assume, let us do a change of variable here, you can set tau plus t by 2 as some other dummy variable t prime. Then you can think of this Wigner-Willi distribution as a transform of the x of t prime with a basis e to the minus j t z times x star of a rewritten dummy variable here. So, your basis function is not just e to the minus j tau z, but also times this. Now, this factor in the basis function comes from the signal, and therefore, Wigner-Willi distribution is sometimes conceived as a transform of the signal with an adaptive basis. The adaptive term coming from the fact that the basis is derived from the signal itself, unlike in Fourier transforms where the basis is fixed a priori. That gives certain advantages to the Wigner-Willi distribution, whereas in the case of Fourier transform or wavelet transform or short time Fourier transform, the bases are fixed and there are some disadvantages, but of course, the advantages is you know the basis a priori, you know their properties. Therefore, once you break up the signal into different components, it is easier to interpret them. Whereas with Wigner-Willi distribution, you do not know the basis a priori, and therefore, you have to interpret everything after performing the transform and keeping the signal in mind. Okay. So, the point here is Wigner-Willi distribution offers excellent time resolution compared with the spectrogram, and likewise in the frequency domain as well. I have a complex sine wave here, plug that complex sine wave into the theoretical definition. You will be able to show that the Wigner-Willi is once again a Dirac in the frequency domain centered at omega naught, where omega naught is the frequency of the signal itself. So, I have an illustration for you of this fact. I have a sine wave, once again I am using the time frequency toolbox, and I show you the Wigner-Willi distribution. It is highly localized. Think of this, obtaining this with the short time Fourier transform. I can do this, but I have to use a very wide window. In fact, only maybe Fourier transforms will give you such kind of resolution. It is exactly what Fourier transform gives you theoretically. So, here there is no concept of windowing. I do not have to break my head on determining what is an appropriate window length and so on. It is all built in. And the main point to remember is that the Wigner-Willi is ideal for chirps. Once again, we can verify this by writing the expression, theoretical expression for a linear chirp. You should be able to see that it is a linear chirp once again, because the phase of this signal is a quadratic function of time. And the Wigner-Willi of this linear chirp is a Dirac. In what sense? It is a Dirac not in the regular sense, it is a Dirac along the line of instantaneous frequency. Earlier when I had a sine, it was a Dirac in the frequency itself, regular Fourier frequency. Now it is a Dirac in the instantaneous frequency. Note that the instantaneous frequency of the signal is alpha t plus omega naught. So, that is exactly what is showing up here, and the distribution is therefore perfectly localized along the instantaneous frequency. Once again, I show you I illustrate this fact here for you using the time frequency toolbox. The FM lin generates a complex linear chirp, and therefore, you do not have to take any Hilbert transform or construct an analytic representation. I have the Wigner-Willi distribution here, it just looks beautiful and very attractive. It is very nice, right? It is too sweet in fact. Compare this with what we have for the spectrogram, or in fact, I would recommend that you also try this with a wavelet, that is generate a scaleogram. Either way, there is a heavy smearing of the energies. In fact, if you construct a scaleogram, you should expect that the smearing will be higher in the high frequency region, because wavelets have poor frequency localization in the high frequency region and good frequency localization in the low frequency region. So, I leave that as an exercise. All you have to do is generate the signal and run TFR scalo, and you will be able to generate the scalogram. Great. So, now what about a modulated chirp? Again, the modulated chirp is special, first of all because the WVD provides an excellent resolution of the modulated chirp. What we mean by modulated is amplitude modulated chirp. I have taken this chirp signal, for example here, and multiplied this with a Gaussian wave, Gaussian amplitude modulation that only exists over this period of time, as a result of which I have this amplitude modulated chirp. The Wigner really looks very nice because it has perfectly localized the frequency as well as the time. Everything is nicely captured. Compare this with what a scalogram computed with a modulate wavelet provides for you. In the scalogram as well, there is nothing to play around as far as windowing is concerned. In spectrogram at least you may have to play around with the window, but again I invite you to compute the spectrogram with different window lengths and see if you can get as fine as an energy density that Wigner really gets for you that I show here, right. Now, the speciality, the second speciality of this modulated chirp with in the context of Wigner-Willi is that this is the only signal for which Wigner-Willi is non-negative in the entire time frequency plane. Great. So, we have a lot of things to boast about Wigner-Willi, but now you have this beast called interference. So, the Wigner-Willi of sum of two sine waves shows interference exactly midway of the frequencies. Now, that is both good and bad, and I will tell you what is the bad news first. The bad news is of course the interference. Once again I illustrate this for you first, and then we will just quickly talk about the theory and wind up. So, I have generated two sine waves of frequency 0.1 cycles per sample and 0.2 cycles per sample. I have added them up, computed the Wigner-Willi. You can see this interference term appearing exactly at 0.25 frequency cycles per sample, whereas the spectrum does not contain it. So, it is always useful to plot the spectrum by the side and the signal on the top, so that you can make meaningful interpretations from the energy density plot, joint energy density plot. Now, why does this happen? Because in general if I have two signals, then the superposition of the Wigner-Willi of a superposition of these two signals involves the sum of the Wigner-Willis of the respective components and a cross term which involves the cross Wigner-Willi term, in fact 2 times the real part of that. Therefore, Wigner-Willi is always real, although I have not mentioned that early on. The Wigner-Willi is always real. It does not mean it is non-negative, but it is real valued. This term here, the third term 2 times real part of W12 is the one that causes the interference. The good news is that I know exactly where the interference occurs. It is not going to occur at arbitrary locations. I will also show you this a small animation in the coming lectures where we try to remove the interference term to show you that the interference always occurs midway, whether in time or in frequency depending on how they add up, and that gives me the key to eliminating the to an idea of how to eliminate the interference term. That is the key, all right. So, with this slide we will draw this lecture to a close, and once again I have a few references for you. These are more or less the same references that you have been seeing. So, what we have learned is what is the definition of Wigner-Willi, how it is different philosophically from spectrogram and even scalogram, and that it has certain very nice features. We have not studied thoroughly all the properties. In the next lecture we will examine the joint energy density for all the properties that an energy density should have. It has some beautiful properties. It is ideal for chirps and so on, modulated chirps, but there are going to be interferences and we have to see how to get rid of these interferences from the Wigner-Willi distribution. Okay, so hope you enjoyed the lecture. We will meet again in lecture 6.2. Thanks.